The distributed request router operates as a stateless intermediary layer within cluster topologies. The primary responsibility of the router is to receive inbound client requests, evaluate routing criteria, and forward those requests to appropriate backend service instances. The router does not retain session state between requests. Configuration parameters include maximum, concurrent connections, timeout thresholds, and backend service endpoint definitions. All routing decisions are deterministic and based solely on request metadata. Request ingestion occurs through a configurable set of listening ports. The router accepts TCP connections on these ports and maintains a fixed size buffer for each active connection. Once a complete request frame is detected, the frame is parsed to extract routing headers. The parsing operation is performed synchronously within the connection handler thread. Malformed frames are logged and the associated connection is closed after a brief grace period. The routing decision process evaluates request attributes against a set of defined routing rules. Roles are stored in memory as an ordered list and are evaluated sequentially until a match is found. Each rule specifies a condition predicate and a target backend instance. Condition predicates examine the request method, path segment, header presence, or source address. The first matching rule determines the target backend. If no rule matches, a default backend is selected or an error response is returned. Backend service instances are tracked within a registry structure. The registry maintains endpoint addresses, health status flags, and availability metrics for each service instance. Health checks are performed periodically by sending keep-alive probes to each registered instance. If an instance fails to respond within the configured timeout, its status is marked as unhealthy. Unhealthy instances do not receive new requests until they respond successfully to a probe. Load balancing is implemented using a round-robin selection algorithm when multiple healthy instances are available for a target service. The router maintains a counter for each service group that increments after each request is forwarded. The counter modulo the number of healthy instances determines which instance receives the next request. This algorithm ensures even distribution of traffic across available instances. Counter overflow is handled through modular arithmetic. Request forwarding occurs after routing decision completion. The router establishes a connection to the selected backend instance if no persistent connection currently exists in the connection pool. The request is then transmitted to the backend without modification of the request body. Response data from the backend is buffered in memory as it arrives. Once the complete response is received, it is forwarded back to the original client connection. Connection pooling reduces overhead by reusing established TCP connections to backend instances. For each backend instance, the router maintains a pool of open connections. When a connection is needed, an available connection is selected from the pool if present. If the pool is empty, a new connection is created. Connections are retained in the pool after use until a maximum idle duration is exceeded. Idle timeout is configured per service group. Response buffering is limited by a configurable maximum size threshold. If a response exceeds this threshold, the router returns an error status code to the client and logs the event. Partial responses are not transmitted. This mechanism prevents memory exhaustion in scenarios involving unusually large responses. The threshold can be adjusted independently for each backend service. Default value is 100 megabytes. Error handling for backend failures follows a deterministic protocol. If a connection cannot be established to a target backend, the connection operation is retried up to a configured maximum number of times. Retry attempts are separated by exponential backoff intervals. After maximum retries are exhausted, an error response is sent to the client. The backend instance status is marked unhealthy and will be excluded from future routing decisions. Request and response headers are processed according to a filtering configuration. Headers specified in the filter list are either removed or modified before transmission. Common modifications include adding router identification headers, updating connection management headers, or removing sensitive information. Header processing occurs after response buffering is complete. The header filter configuration is reloadable without service restart. Timeout enforcement operates at multiple layers within the router. Connection establishment has a separate timeout distinct from request transmission timeout. Response reception also has its own timeout period. If any operation exceeds its timeout, the connection is terminated immediately and an error response is sent to the client. Timeout values are specified in seconds with millisecond precision. All timeout operations use monotonic clock sources. Logging is performed asynchronously to avoid blocking request processing. Log entries include timestamp, request identifier, routing decision details, backend selection, and response status. Log output is written to a circular buffer with configurable size. When the buffer reaches capacity, oldest entries are overwritten. Log levels can be configured to control verbosity. Debug level includes full request and response payloads. Configuration reloading is supported without service termination. New routing rules can be deployed by writing updated configuration to a monitored file path. The router periodically checks this file for modifications. When changes are detected, the new configuration is loaded into memory and validated. If validation succeeds, the configuration is activated atomically. Requests in flight continue using the previous configuration during the reload process. Metrics collection captures statistics about router operation. Metrics include request count, response time percentiles, error rates, and connection pool utilization. Metrics are calculated over fixed time windows and exported periodically. Each backend service has separate metric counters. Metrics are exposed through a dedicated endpoint for consumption by monitoring systems. Metric storage uses circular buffers with retention of 1 hour of data. Connection lifecycle management includes explicit cleanup procedures. When a connection is closed, its associated state is removed from the pool. Periodic cleanup runs at configurable intervals to terminate idle connections. Connections that have been idle longer than the configured threshold are terminated regardless of usage status. This prevents resource accumulation in long-running deployments. Cleanup operations are rate-limited to avoid simultaneous termination of many connections. Shutdown procedures ensure graceful service termination. When shutdown is initiated, no new requests are accepted. Existing connections are allowed to complete current requests up to a grace period timeout. After the grace period expires, remaining connections are forcefully closed. In-flight request processing is terminated and error responses are sent to affected clients. All connections in the pool are closed. The shutdown process is logged with timestamps.